Here is a language model. Not a diagram of one. All of it. Every matrix, drawn at the size it actually is. You have almost certainly seen this explained before, and I would bet you saw it explained in pieces. One diagram for the embeddings. A different one, drawn by a different person at a different angle, for attention. A third for the feed-forward network. Every one of them correct, not one of them the same picture. So you end up with a dozen views and no object, which is why people who can recite what attention does still can't tell you where it sits. There is a second problem, and it is quieter. Almost every transformer diagram draws attention and the feed-forward network as two boxes of about the same size. They are not the same size, they are not close, and they have been getting further apart every year. So, one object, drawn at its real proportions. Every part in the place it actually sits. And here is the route we are going to walk through it, in the order the model actually uses it. Tokens, the embedding table, position, attention, the feed-forward network, the stream running past both of them, the mask, the unembedding, and the thing that finally picks a word. One machine, and by the end, every part of it will have a name. Let's put something in. The capital of Taiwan is. The model never sees that sentence. It cannot. It is a function from numbers to numbers, and there are no letters anywhere inside it. So the first thing that happens is that the text is cut into pieces from a fixed list. For this model, that list has 151,936 entries. Every piece of text you ever send it has to be spelled using those. Our sentence comes to 5. The capital of Taiwan is. That looks like words. No, it is not words, and the difference matters more than it sounds. Here is the same list applied to one word, strawberry. In the middle of a sentence, strawberry is a single token, one number. At the start of a sentence, the same word is 3, star, aw, berry. Same letters, same meaning. Different number of tokens because one of them has a space stuck to the front and the other doesn't. That is not a bug, and it is not a rare edge case. It is what tokenization is, a compression scheme that was fitted to a pile of text, and it has no idea what a word is. It is also, quietly, why models are bad at counting letters. If the model never receives strawberry as letters, asking it how many R's are in it is asking it to remember a fact about a symbol it cannot see. Numbers get it worse. The number 4096, a number this model is built out of, arrives as 5 separate tokens. A space, then 4, then 0, then 9, then 6. Every digit, always, on its own, which means arithmetic is not something the model reads. It is something the model has to reassemble. One more, because it will matter later. The model's own name, Qwen, is 2 tokens. Whatever you put in, this is what comes out. A list of integers. That is the input. Everything past this face is arithmetic, so let's take them in. So we have 5 numbers. Now they have to become something a matrix can multiply. There is a table. 1 row per token in the vocabulary, and each row is 4,096 numbers long. Token 5,000 and something? Take row 5,000 and something. That is the whole operation. No computation, a lookup. And that table is not small. 151,000 rows, 4,096 wide, is 622 million numbers. This model keeps a second copy for the way out, which we'll get to. Together they are about 15% of everything it has. 15% of a language model is a lookup table. What comes out is a vector. 4,096 numbers, which you should think of as a direction rather than a list. And that space has structure, which is the part worth pausing on. Rows for related tokens end up near each other because they got used in similar places and training pulled them together. Not because anyone arranged them. The table starts as noise. The arrangement is a residue of what predicted well. Now, a problem. Nothing so far knows about order. Taiwan is the capital of, and the capital of Taiwan is, are the same 5 rows of the same table. The original transformer fixed this by adding a position vector to each embedding. Add a little something to say, you are word 3. Almost nobody does that anymore. What this model does instead is rotate. Position isn't added to the vector is turned by an angle that depends on where the token sits. It's called rotary position embedding, and the reason it won is worth 1 sentence. Rotating by position means the angle between 2 tokens depends only on how far apart they are. not on where they are, which is the thing you actually wanted. Relative position for free without a single extra parameter. So text became numbers, numbers became directions, directions got turned to record their order. Nothing has been understood yet, nothing has looked at anything else. That starts now. Pull back. This is the model, 36 of these. And they are the same shape, not similar, the same. Same layout, same sizes, same operations, 36 times, each with its own numbers. That is the entire architecture. One function applied over and over to a vector that keeps getting rewritten, which means if you understand one of these, you have understood the model. Everything else is a matter of how many, and it is worth being precise about what the same means because it is stronger than people expect. Not a repeated pattern with variations. Block 4 and block 31 have the same number of heads, the same widths, the same operations in the same order. Nothing about the structure changes with depth. Only the numbers inside differ. There is no early layer design and no late layer design. If early and late layers end up doing different jobs, and they do, that is something training produced, not something anyone built in. Each one holds 193 million parameters. And inside, there are exactly two things: attention and the feed-forward network. Everything you have heard about transformers is about those two boxes and the wire that runs past them. Start with the smaller one. Every vector so far has been alone. Taiwan was turned into a direction without any reference to capital or of or anything else. Attention is the only place in the entire model where one position gets to look at another. That is worth sitting with. 36 blocks, hundreds of matrices, and the mixing happens in exactly one of them. Here is how. The incoming vector is multiplied by 3 different matrices, producing 3 different vectors from the same input. They get called query, key, and value, and the names are a database metaphor that half helps and half doesn't. The useful version, the query is what this token is looking for. The key is what a token offers. The value is what it actually hands over. Every token's query is compared against every token's key, a dot product, one number per pair. High number, these two are relevant to each other. Low number, ignore. Take our sentence. The last token, is about to have to produce something. Its query goes out against all 5 keys. Whatever Taiwan is offering, wants it, because a sentence of that shape is about to need a place name. So that pair scores high, and the others don't. There is one detail in the middle that looks like housekeeping and isn't. Before the squash, every score is divided by the square root of the head width. Dot products of long vectors get large, and a squash-fed large numbers saturates. It stops being a soft weighting and becomes a hard pick, with almost no gradient left to learn from. The divide keeps it soft. Then those numbers are squashed into weights that sum to 1, and each token's output is the weighted average of everyone's values. That's it. That is attention. Everything else about it is an optimization. Except for one thing, which is not an optimization, and which shapes the whole model. Half of that grid is thrown away. A token is not allowed to look at anything that comes after it. Not damped, not downweighted, set to -infinity before the squash, so it contributes exactly nothing. Because the model is being trained to predict the next word, and a model that can see the next word learns nothing at all. That triangle is why text generation goes left to right. It is not a philosophy about language, it is a mask. Now the optimizations, because 2 of them are the difference between a model you can serve and one you can't. First, this doesn't happen once per block. It happens 32 times in parallel on different slices of the vector. 32 heads, each 128 numbers wide. Together they are the same total width as the vector. This is not extra capacity, it is the same capacity cut up. And the reason to cut it up is that one attention operation produces one weighted average, one opinion about what matters. 32 narrow ones can hold 32 different opinions at once and add them all back. Now the honest part, because this is where explainers usually hand you something tidier than the truth. You will have seen heads described as having jobs. This one tracks syntax, that one resolves pronouns, this one copies rare words. Some of that is real. There are heads that have been isolated, poked at, and shown to do a specific identifiable thing, and it is genuinely some of the best work in the field. But it is a minority of heads in a minority of models, and it is much harder than the clean examples make it look. Most heads do not decompose into a sentence. The safe version is the boring one. 32 independent chances to weight the same context differently, and the model uses them for whatever training pressure made useful. Second, and this one you can see in the shape, there are 32 queries, but only 8 keys and values. 4 query heads share one key value pair. It's called grouped query attention, and it is not about quality. It's about memory. Because when this model generates text, it does not redo the whole calculation for every new word. It keeps the keys and values it already computed and reuses them. That store has a name you have probably heard shouted at you by an error message, the KV cache, and it is enormous. For this model, every single token you keep costs 144 kilobytes. Fill the context window, and the cache alone is about 5.5 gigabytes for one conversation. Not the weights, the conversation. If you want the long version of why that number decides what the whole industry ships, I spent a good chunk of the diffusion video on it. It's linked above. Cutting keys and values by 4 cuts that bill by 4. That is the entire reason grouped query attention exists, and it is why the shape you are looking at is lopsided. So attention mixes positions, and it pays for the privilege in memory. And for all that, it is the smaller half of the block. This is one block. Attention, and then the feed-forward network. Almost every diagram you have seen draws those two at about the same size. Here they are at their real size. 193 million parameters in the block. 151 million of them are in the feed-forward network. 78%. Attention gets the other 22. It was not always this lopsided. GPT-2's feed-forward network was exactly 2/3 of the block, and 2/3 is the number most people still quote. 2 things moved it. Gating added a third matrix where there used to be 2, and grouped query attention, the thing we just watched, cut the keys and values to 1/4. Nobody set out to make the feed-forward network dominant. It is a side effect of 2 unrelated efficiency decisions that happen to push the same way, which means the standard diagram is not just wrong, it is getting wronger. So let's go inside the thing that won. 4,096 numbers arrive. One vector, lifted off the stream. The way up is not one matrix. It is 2, side by side, both reading that same vector. Each one projects it up to 12,288. Every one of those 12,000 is a weighted sum of all 4,000 inputs. Then a non-linearity, and it lands on only one of the 2. That squashed one is the gate. The 2 are multiplied together, element by element. Where the gate is near 0, that unit is shut, whatever the other projection wanted. And the squash in the middle mixes nothing. Each number is squashed on its own. No unit ever sees another one. Every bit of mixing in this box is in the matrices. Then the third matrix brings 12,000 back down to 4,096. That is the whole thing. 2 matrices up, a squash, and a multiply between them, 1 matrix down. Older models had 2 matrices here and no gate. GPT-2's feed-forward network is exactly that. Gating is worth 1% or 2% of loss, and it is in essentially every model shipped since 2024. It is also, on its own, most of the reason this box is 4/5 of the block instead of 2/3. Now, what is it for? The honest answer is that this is one of the least settled questions in the field, and I would rather tell you that than hand you a tidy story. The tidy story is that these are key-value memories, that some of those 12,000 units fire for specific facts, and the second matrix writes those facts back out. There is real evidence for it. There is also a paper from 3 weeks ago that complicates it badly. It trains transformers with no feed-forward network at all. Just attention, stacked deeper with the parameters it saved. Matched on parameters, the gap is 0.006 nats. A nat is the unit language models are scored in, how surprised the model was, on average, by the next token, and lower is better. 0.006 is about 1/4% of it. Those models are small, under 90 million parameters, and the paper says so itself. But the finding underneath is sharper than the headline. What the feed-forward network is worth at matched size is knowledge. The gap shows up on the tokens where context gives you nothing and you have to have memorized the answer. So, the parameters matter enormously. The particular shape we put them in may matter much less than the diagram implies. 4/5 of the block, and we are still arguing about what it does. Come back out. I have been describing attention and the feed-forward network as things the vector passes through. That is the standard picture, and it is wrong. The vector does not go through them, it goes past them. Attention reads the stream, computes something, and adds it back. The feed-forward network reads the stream, computes something, and adds it back. Neither one replaces anything. That line is called the residual stream, and it is the most consequential thing in the architecture that almost no diagram gives a name to. It means the vector arriving at block 36 still contains the embedding that was looked up at block 0. Nothing was ever overwritten. Things were only ever added. It also means every block is reading whatever every previous block wrote. 72 components, all writing into one shared channel in a fixed order, which raises an obvious question that took the field an embarrassingly long time to take seriously. How does one vector of 4,000 numbers carry everything 72 components want to say, without them writing over each other? The short answer is that it doesn't, quite. There is good evidence that models pack far more features into that channel than it has dimensions, by letting them overlap and tolerating a little interference. Which is a strange thing to build a system on, and it is not obvious it was ever a design decision so much as something that worked and never got revisited. The mechanism is embarrassingly simple, x plus f of x, and it has been essentially untouched since 2015, which in this field is a geological age. There is one piece of housekeeping. Adding 72 things to one vector makes it grow, so before each block reads the stream, the values get normalized, rescaled to a sane size. Normalize before, add after. The stream itself is never touched. Which is why the last thing this video does, in a minute, is show you 3 different ways people are trying to change it, and why changing it is so much harder than changing anything else. Time to answer the question the comments would ask anyway. Encoders, decoders, encoder-decoders. 3 words that get thrown around as if they were 3 architectures. They are not 3 architectures. Look at what changes. It is the mask. That's it. That's the fork. Let the triangle go, and every token can see every other token in both directions. That is an encoder. It cannot generate, it has already seen the answer, but it produces a representation of a whole passage at once. BERT in 2018 was that. So is most of what quietly runs your search results. Keep the triangle, and each token sees only what came before. That is a decoder. It can generate, because predicting the next thing is the only job it was ever allowed to have. Bolt one to the other, an encoder for the input, a decoder for the output, with attention running between them, and you get the original 2017 transformer and T5 after it. For a while, that middle option looked like the future. Translation is genuinely a 2-sided problem. It's also, as it happens, what the first big mixture of experts language models were. G, Shard, and Switch were both encoder-decoders. I got that slightly wrong in the Mixture of Experts video, and it's the kind of thing worth correcting rather than quietly leaving. But the middle option lost, and the reason is not subtle. An encoder-decoder needs to know where the input stops and the output starts. A decoder does not. It has one stream of tokens, and it predicts the next one forever, and it does not care whether a given token came from you or from itself. That turns out to be the more general machine. Instruction, conversation, code, tool calls, they are all just tokens in front of other tokens. So every model you actually generate text with today is the right-hand branch. Same block, same stream. One triangle of mask. Encoders did not die. They went to work somewhere quieter. Embeddings, retrieval, re-ranking, where you want to read a whole thing at once and never write anything back. We are at the top of the stack. 36 blocks have read and written the stream. What comes out is a vector, the same 4,096 numbers we have had since the lookup, rewritten 72 times. It is a direction. It is not a word, and there is nothing about it that looks like one. So it gets multiplied by one last matrix, the mirror of the lookup table from the start. 4,096 numbers in, 151,936 out. One score for every token in the vocabulary. Those are called logits, and they are the actual output of a language model. Not text, a number for every possible next piece of text. Softmax turns them into probabilities. And then, something that is not the model picks one. This is the part that gets skipped, and it causes more confusion than any other single thing about these systems. The model does not choose a word. It produces a distribution over 151,000 options, and a sampler, ordinary code, no learning in it, draws from that distribution. Temperature is a knob on that draw. Turn it down, and the sampler takes the top of the distribution nearly every time. Turn it up, and it flattens, and unlikely tokens get a real chance. Same model, same weights, same input, different text because a different sampler drew from the same numbers. Which means when people say a model is creative at high temperature, they are describing a property of about 40 lines of code sitting outside it. Temperature is not the only knob, and the others are blunter. Top P throws away the tail of the distribution before drawing at all. Set temperature to 0, and there is no draw left. It takes the single highest score, every time. That last one is worth knowing because it is what most benchmark numbers are measured at, and it is not how the thing is usually run. Then the chosen token goes back to the bottom, gets looked up, gets rotated, and the whole thing runs again. Every token you have ever seen a model produce cost one full pass through all 36 blocks. The 300 words of an answer are 300 passes. That is the loop. That is all of it. Everything I have shown you is the shape of a model from 2025, and I have been calling that deliberate. Here is why. It is the last version of this architecture simple enough to draw honestly. What has happened since is not a new architecture. It is 3 swaps into the object you are now looking at. Swap 1. Take the feed-forward network, that 4/5, and cut it into a few hundred smaller copies. Then, for each token, run 2 or 3 of them and skip the rest. The parameter count goes up enormously. The work per token barely moves. That's mixture of experts, and it has a much longer and stranger history than anyone tells you. It goes back to 1991, and the version people are excited about now is almost the opposite of what was invented. That is a whole video, and it is linked above. Swap 2. Attention. We saw why the KV cache is expensive. Grouped query attention shaved it by 4. That was not enough, so the current generation attacks the operation itself. Here is the configuration file of a Frontier Open model from this year. Look at what it says about its own layers. 3/4 of its attention layers are not attention as I described it. They are a cheaper operation with a fixed size memory, and every 4th layer is the real thing, holding the whole picture together. Swap 3, and this one is not a component. It is the loop. Everything about that output loop assumed 1 token at a time, left to right, because of the mask. There is a family of models that does not do that, that generates a whole block of text at once and refines it. And in the last couple of months, somebody took a normal model of exactly this shape and converted it into one of those, for under 1/10 of the original training budget. I made a video on where that whole fight stands, also linked above. 3 swaps, the feed-forward network, the attention, the loop. And notice what did not change, not once, in any of them, the residual stream. Every one of these keeps x plus f of x, and quietly assumes that a shared additive channel is the right way for 72 components to talk to each other. That assumption is 11 years old, and there is now serious work trying to break it, which is a hint about where the next one of these videos goes. Pull all the way back. Same shot we opened on. Tokens at the bottom, because it cannot read. A lookup table, because a number has to become a direction. A rotation, because nothing else knew about order. 36 identical blocks. Attention, which is the only place anything looks sideways and which pays for it in cache. The feed-forward network, 4/5 of the parameters, still argued over. A stream running past all of it that nobody ever draws. A triangle of mask that decides whether you have a decoder, and a matrix at the top that turns a direction back into 151,000 numbers for something else to choose from. One object, not a dozen diagrams of one. If a specific part of it is what you actually came for, 3 of them have their own videos, all linked above, where the feed-forward network goes when it is cut into experts, what happens when a model gives up its eyes, and what happens when you throw out the loop entirely. And if there is a part of this you would want taken apart properly on its own, say which one. That is genuinely how the next one gets picked.